So I'm really happy to have Glenn here again today because we're going to solve all the problems of the universe. We have stacks and stacks and stacks of papers and ideas, and we decided we would narrow it down to just one thing. We're going to look at one of Glenn's favorite ideas, and that comes from John Wheeler, It from Bit. Before I bring the paper up, Glenn, is there anything you want to say about it?
I would recommend it to anybody who is a diehard physics person to take a look at it if they haven't seen it in their life. It's short, and I think it's accessible and important.
And it has a lot of implications, right?
Yes.
Yes. Okay. Well, so let me bring it up here. Get sharing. So would you say that the most important thing is these 3 questions and 4 no's and 5 clues, or do you want?
Yes, that's where I would start.
Okay.
Yeah, I think those are accessible. You don't need to know a whole lot of physics to ponder some of these. So this is, you're looking at the beginnings of, okay, settle down now.
Yeah.
Of the whole black hole entropy, Hawking radiation, the whole industry that you'll now, if you go on the web and TED Talks, and you'll hear, started with this It from Bit.
So how long ago was this paper published? Do you remember?
I want to say 60s or 70s.
Okay, so quite a few years back.
I could be totally wrong. Bekenstein was, I believe, John Archibald Wheeler's grad student at the time. And it started out as a
doesn't say what year.
Kind of a joke question that John had asked about dropping 2 hot and a cold cup of tea into a black hole. And that took on a life of its own and grew. But what is always
so this whole idea of his in this paper came out of them bouncing that question around.
Right. That a bit is actually the fundamental ontology. I think that's the word of what is the stuff the universe is made of. It's made of information in this formulation, this way of thinking. And information becomes a physical object by the process of measurement or interaction or observation. So what they've done is they've created, the universe is now a soup of information out of which the physical world happens by observation. And I don't want to get any farther than that because it can be quite a swamp to step into. But the assumptions that John Wheeler brought to the table when he began all of this have long since been forgotten. If you read any of the new papers being published now, these assumptions have gone, and no one has gone back and looked at them and why. So
okay, well, let me just explore that for just a second. So people are perfectly willing to stand on his shoulders to pursue their careers in black hole theory.
Right.
Right. But
right.
They're not willing to understand what gave him that gigantic perspective that
right.
allows them to stand on the shoulders. Right.
Right. So that's always the admonishment in physics and science in general. Go back to first, principal sources beginning, because the people who first discovered something were looking at something completely different on the way up than you see in your textbooks looking back down. And so a lot of the history, the inspiration, the the connections that the original thinkers motivated them to come up with an idea get erased. The idea gets cleaned up and presented. You might imagine a cathedral. They build it and then they take down all the scaffolding, and you're just left with this beautiful building, but you don't know how they got there in the first place. Always go back to first sources and try and see what they were seeing at the time. The four no's are really interesting. The No Tower of Turtles, first off, a religious reference, to anyone who's familiar. And this tells me that John Wheeler was thinking in terms of that there is a theory of everything. There is a fundamental theory out of which everything gets explained. If you go out in the physics community, people actually reject that, because to believe that there's a theory of everything is the same as saying God made it all. That's one of the explanations to the problem of fine-tuning. We have 24 plus fundamental constants in nature that we've experimentally determined them. And once you do that, measure them, put them back into the theory, theories give you these amazing answers to as accurate as you can experimentally verify. But where those numbers came from? Well, one, there's a God who made the universe just right for us to be here, because I'm sure you've seen a lot of the anthropic principles that people have gone back and looked at all of these constants and say if they were off by 1%, 2%, 10%, life as we know it wouldn't exist. The cosmological constant is the famous one, because that is 0.000 102 zeros and then a 1. If that number is any different, then we don't exist. So how do you deal with that? Well, then you get the multi-universe. It's all random. It was all by accident. So in order for us to exist, Mother Nature has probably experimented a billion times. And out of all the experiments, we happen to be the lucky one. So
that's so just the way you said it. I mean, I understand that the language just forces a person into that kind of a box. But I mean,
I know
Mother Nature was experimenting.
Well, it's just random. Now, if you're an atheist and you don't want to believe that there's a God, then you just have to throw everything out to random chance. And the universe is just a bubbling sequence of possibilities, and once out of eons of time, we get lucky.
Okay, but you still, right there, you needed possibilities, you needed time, you needed.
But what's time?
At bare minimum, you needed energy, because even if you don't have the resource of matter to work with, you have to have energy. So I mean, there's already some prerequisites there just to start the experiment.
I know there's a whole multi-universe has a lot of problems that people don't want to talk about, but it is a really big rug you could sweep a lot of problems under.
Well, I mean, I've even heard some of those people talk about the universe generator. It's like, okay.
Okay.
That seems like a much bigger problem than just saying that there's a God.
But, this is just anecdotal, is watching the world of physics, that the same people who reject God as or just some intelligence, some outside intelligence, external intelligence that's separate from the physical universe, creating it just right, will also reject the notion that there's a theory of everything that gives you all these numbers just by the way the theory works.
Well, okay, so then you need to explain to me then, if John Wheeler was an atheist, then why do you say that that there is an implication behind the No Tower of Turtles, that he believed that there must be a theory of everything?
Well, it's a comment somebody at Jordan Paul's Jordan Peterson meetup at Sacramento. He asked me one time, he said, how do you know that your Christian faith doesn't make you see things in physics that aren't there? And that's a good question. That's a valid question. But my answer in turn is that, well, how do you know that your atheism is not blinding you to see things that are there? And I don't have an answer for it. I think it's something to contemplate. But I feel that being a Christian doesn't make it hard to be a physicist. I think it frees me up, because I don't need physics to take the place of God. And what I had a sense when I'm reading this paper with John Wheeler is that he is searching for God. He's trying to create something that, like God, out of physics. But he's possibly not realizing that that's what he's doing. You've sensed that when people talk about, well, you don't need a religion to have morals. But then you but then you realize, well, you're borrowing. I think I'm losing the trail, but I think you know what I'm talking about.
Well, I do. You had mentioned slightly, just before we started recording, you had mentioned that this No Tower of Turtles kind of relates to Richard Feynman's idea of the world being kind of like an onion, where you keep peeling away the layers, and you get deeper and deeper down into what reality is.
Yeah, for Feynman, physics to him was like these onion layers. Each layer of abstraction, as we solved the theories and the problems, would reveal yet another layer of abstraction under that. And my impression from listening to him at the time was that is one alternative to the job of physics, is that you see it as this infinite layer of abstractions. As we understand each a new one, then we discover one yet more hidden underneath that. Whereas the Archibald Wheeler, he's saying, no, there is a first one, and everything comes up from that.
Because the old Tower of Turtles story was that the idea would be that, I think it's an apocryphal story about some woman that went up to a physicist afterwards and was asking some question, and she said, no, sir, you're wrong. The universe, the world stands on the back of a turtle. It's founded on the back of a turtle. And then
I think it might be an elephant rides on the back of a turtle. And
okay. And then what's under the turtle? And she says, you can't fool me, young man. It's turtles all the way down. Mm-hmm. Because she didn't have an answer for what was supporting the turtle. Right. But so John Wheeler is saying there's no Tower of Turtles. It's not an infinite regression. It goes back to a certain point. There's
a certain place where the laws of physics start, and that's it. There's no more onion layers to peel off. Mm-hmm. Well, that's a bit sounds like Genesis, creation ab initio, out of nothing. Mm-hmm. No laws. In other words, he felt that the laws of physics came into being with the universe. Which I don't know, that's debatable. Then he said no continuum. And that has always struck me, because that would imply that he was saying the universe is finite and discrete, which sort of makes sense if you're going to talk about information in bits and ones and zeros. It implies that there must be some pixelation, there's some coarseness to the universe, so that you can talk about bits or voxels or pixels, however you want to use the term, in no space and no time. So, but you take these, and if you look at all of the papers that have come on, all of the research, that's all based on calculus, mathematics of continuous and differentiable functions. All of our laws of physics are using calculus. Those are all imply the continuum. If you take away the continuum, you lose calculus, you lose string theory, you lose all sorts of stuff. I'd love to see that explored by someone who has a greater knowledge than I do. But
Well, I mean, it would be fun to look back into Matthew Peugeot's book on time and space, his book on the language of creation, because he has very thorough explanations about time and space.
Right.
That space is discrete. That he says that time is continuous, but in Wolfram's model, both time and space are discrete, and they are discrete from each other, and then each of them internally is discrete.
Right, and there's other possibilities that come up as well. And then I noticed John talks about consciousness. Now, this is the big unsolved problem in physics: is where do physicists come from? And that's a joke. But the whole notion of observation and measurement, but quantum mechanics can't explain where the observer comes from. That is a big, big problem. No one wants to talk about it, and everyone just walks around it. But it kind of sits there waiting for someone to tackle it.
Well, what I hear some of them say, which I think is kind of humorous, is no, you don't need a human observer. It can be done by a mechanical device.
Yeah,
well, where did the mechanical device come from?
Or what? How did it come into being? Something.
Well, to me, over here on this list of 5 clues, the second one is. That's the whole story right there. No question, no answer.
Mm-hmm.
So it reminds me of one time I was listening to Hans Zimmer, who is the guy he does a lot of soundtracks for
music.
Yeah, he did the soundtrack for Interstellar. And he was talking about the creative process, and he said, the way that I write music is that I start with a phrase that asks a question. Mm-hmm. Because if I don't ask the question, then there's no place to go. The question elicits an answer, right? And then the answer elicits another question. And so then you get a process going. But if there's no question to begin with and no answer, then no universe.
Yeah. So you can have fun with John Wheeler stuff and think about it. But if you get back to the theory of everything, TOE, any theory of everything is going to have to explain where the observer comes from. Otherwise, it's not a theory of everything. But once you have come up with a physical explanation for where observers come from, you have given an explanation for consciousness. And you've also shown origins of life. That was a while back, you did the Stairway to Life video.
Yes.
Stepmother and Tan.
Mm-hmm.
And the question is origins of life a physics question? Some people say yes. And, I'm in the camp that says yes, but other people that say no. But if physics is going to explain the origins of life, it has to explain consciousness, intelligence. That is the big missing link. Physics is not complete. A loop, right? Between the observed and the observer is a connection, is this loop that's not been finished in physics, and it's an open. But if you have a theory of everything explains us, then you're going to have a theory that's going to start sounding a lot like religion. There'll be a lot of crossovers. I think Jordan Peterson, once remarked that when you dive deeply enough into human psychology, you reach a point where the spiritual, theological religion becomes the only language you have to work with. Now imagine you have a theory of everything that explains consciousness. Then you're going to have a physics that's starting to sound a bit like theology. I'm not sure how the world is going to deal with that possibility. But it's something to think about. It's real.
Well, since you brought up Jordan Peterson, let me look at this little clip right here of him talking to Roger Penrose.
Mm-hmm.
I need to check and make sure that I optimize sound. Okay. Well, it always happens.
Yeah.
This is, I mean, I have to apologize for people who are listening and not watching. This is another episode of Karen being completely lame with the internet. Somebody mentioned the other day, they said, my favorite part of all your videos is when you screw up on the share screen. So anyway, here we go.
I think that's
I'm
what I'm trying to
curious
say.
though,
Yeah.
too, because in some sense, and I could obviously be wrong about this, but the physical reality seems to constrain the mathematical possibility, because there's only some mathematical rules that govern the behavior of actual objects, even though there's all sorts of possible mathematics that could govern the action of all sorts of hypothetical objects. Right? So imagine if there's an underlying, I can't help but think that this is associated with this many worlds idea, but if there's an underlying metaverse of mathematical possibility, you get the emergence of something like, well, what would you say? One concretized exploration of that possibility space, and that now establishes a relationship between one element of that mathematical possibility space and well, in reality itself, doesn't exhaust the search space, but and it seems to me that that's analogous to this tiling problem in some sense.
Okay, I don't want to go into the tiling problem.
No, that's a
Yeah. But I do want to talk about this statement that he said, where it's emergence of something like one concretized exploration of that possibility space. And that now establishes a relationship between one element of that mathematical possibility space and reality itself. I think he got that turned around. I think the relationship between one element of the mathematical possibility space and reality is the relationship of the observed and the observer. And then from that emerges a concretized exploration of the possibility space.
Yes, I come at it from a different point of view.
Okay, go for it. You're the physicist.
Well, I come at it from the theory of computation.
Mm-hmm.
Is it Ellis? Okay. There is a physicist out there who advocates, and I think he's not the only one.
I think it's George Ellis.
George Ellis.
Yeah.
That algorithms have a reality. They are just as real as physical objects. And I understand why he thinks that way. Because if you look at in the theory of computation, you'll run across Chomsky's hierarchy of languages. And for every level in his type in his hierarchy, in which there's a lot of intermediate levels as well, there's a physical structure that will act as a computational system that will recognize that language. There's a one-to-one relationship in the world between software and hardware. If there's a language is the connection. And I always keep wondering, you go back to the Word, and the Word was with God, and the Word was God. And the Word became flesh and dwelt among us. There's a connection between algorithms, in abstract language of mathematics, words, sentences, grammar, and the physical objects which recognize those languages, accept them is the word. And a computational structure that recognizes something in the language will take that language algorithm and turn it into a physical object or a physical action. So the computational structure is the connection between the abstract realm of the forms, if you want to call it in the Plato sense, and something physical in the physical world.
So the computational structure recognizes the algorithm and turns it into a physical structure?
Right. See, remember we talked about, computation is a sequence of choices based on a set of rules. And so a piece of sheet music is a set of rules. The computational system happens to be the musician who takes that set of rules and turns it into sound. Architect's drawings, again, is equivalent to source code. It's just an idea. I mean, the music started out in somebody's head, not even physically in the form of music notes. So you can think sheet music is a form of language. That's why I want to get away from this notion that information is ones and zeros. It's not binary. It could be a lot of things. Sheet music can be a language of symbols that is telling you how to make a sequence of choices that take what was in somebody's head, Mozart's head when he thought of it, and make it a sound that you can hear now. 300 or 400 years later after his death, you can hear what was in his head. An architect dreams of a building, it puts it into drawings. And then computational devices like plumbers and carpenters and electricians come in, read the source code, the language, it's a formal language, and convert it by the choices they make. They're trained on to make good choices, take those ideas and turn it into a physical reality. So
there's 4 parts there, not just 3, right?
Okay, well,
I
haven't counted them.
Well, so the computational structure recognizes the algorithm or the language,
right,
and turns it into a physical structure,
mm-hmm.
or something that is sensible,
right?
Like hearing a symphony that would attack our senses, so it's physical in that sense.
Mm-hmm.
But there's one more part. If I'm the musician takes the sheet music and turns it into something that I can listen to. But where did the sheet music come from in the first place? Where did the algorithm come from? Where did the language come from? Where did
this is the magic?
That's the 4th thing, right?
Yeah. So I've heard that the story. I don't know if it's true or not. I'm not grounded in music history. That Mozart basically wrote things first draft. That he was basically taking dictation in his head. So he heard the music and he was able to convert it into notes on a piece of paper. That's a formal language in the abstract mathematical sense. Sheet music is a formal language. Now that's written down, that can be copied. Then you imagine a musician as a computer. They take the formal language, the source code, and by the sequence of choices they make, they've been trained, they can take that sheet music and turn it back into sound. Now you, as someone listening to it, can now hear what was in Mozart's head. And most importantly, if the symphony is done right, not only will you hear the notes, but you will hear the emotions. And I always liked that Chris Petkow, he did that symphony of choices over time.
Oh.
And each of the instruments, I like to think, is playing it's a computational device playing a formal language. But if you get enough instruments playing in the right order, synced up just right, with something a little extra, all of that strict technical process becomes a symphony which you hear, and now you experience it at an emotional level. So that to me is telling me, how to say, the whole is greater than the sum of the parts.
Mhm.
Am I making sense?
Oh, absolutely. I mean,
Yeah.
so my brain goes off in a lot of different directions. And when you said that the whole is greater than the sum of the parts, I immediately started to think about some of the stuff that I've been reading and you've been reading from Wolfgang Smith, because I'm going to have a conversation with him next week. And when he's talking about the whole being greater than the sum of the parts, the implication is wherever there are parts, there is a whole that's greater than the sum of these parts.
It could be, yeah.
Yeah, well, but so I started to think about, well, how does how would what would a dog need in order to be able to level up and communicate or understand a human being? And then I thought, well, what would a slug need in order to level up and communicate or understand a dog? And I mean, you could, because we can investigate downwards.
Mm-hmm.
We can we can put things into parts and investigate downwards, looking at them downwards. And in some sense, it's what Wolfgang Smith talks about when he talks about irreducible wholeness has the capacity to effect a vertical causation downwards.
Yes.
And so I'm an irreducible wholeness, so I can act on the world and cause change.
Mm-hmm.
But an ant is also an irreducible wholeness. And so there's a certain kind of ant that farms aphids. And so it gathers all the little aphids. It makes a little barn for them using some sort of thread that it can spin over some leaves, and then gathers in all the aphids and sort of takes care of them, because then it gets the milk out of the aphids. And so that ant is an irreducible wholeness effecting a vertical causation downwards. But then that also implies that there must be some vertical causation coming into us.
Yep.
Right.
Well, the ant is part of a colony. And the colony, an ant colony can be treated as a single life form in its own right. That's where I get intrigued, that the ant colony displays an intelligence that no single ant possesses. It's an emergent intelligence. So the ants they have a set of rules, but they also have a social order. So whenever you see some kind of strong emergence, there implies a social order. So we're part of something bigger ourselves. So society, culture. I've often thought Jordan Peterson should talk to Cesar Hidalgo rather than Roger Penrose, because Cesar Hidalgo gets the notion of collective consciousness, distributed intelligence, that we as individuals are all part of a greater collective system, that together we can bring and solve problems that no single human being by themselves could. So we are part of something yet bigger than us, and we respond to that, and in turn it reinforces the society we live in.
Well, so that seems to me one way in which there is something bigger than us, but that collective intelligence is very different than what you were talking about when you were describing Mozart.
Yeah.
Right? Mozart, that was more like a one-on-one relationship with some.
But Mozart was part of a greater intelligence, because someone had to want to listen to his music. There had to be musicians who worked, could actually make a living at it. The fact that Mozart music survived is telling you that there's a much bigger collective consciousness in society that values music enough to pay people to practice at instruments, to learn how to play it, to record it, to maintain it. There's a bigger picture there. That's what Cesar Hidalgo would point to. Yeah, in order to maintain that level of culture, that creates works of art and music requires a trust network, a collective consciousness, and a corresponding trust network, which accompanies a large number of people over generations, spanning both time and space. I think dogs interface with us because they also have a social order. And there is a Venn diagram of human social order and dog social order overlaps enough that we can relate to them. And I think to some degree they understand our language and we can understand them, because part of our language is centered around the social order we live in. Right. That's just rambling.
Well, one of the ways that Wolfgang Smith was talking about the vertical causation issue is, part of his idea of vertical causation is that there is some sort of realm, whether it's inside of our consciousness or whether it's accessible by our consciousness, that he calls intermediary. Mm-hmm. And he says that we can investigate downward in scientific realms, but if we want to investigate that intermediary realm, the only way is to actually be the observer. For the scientist himself to be the observer in the intermediary realm. And he says one of the ways in which that has happened in history is alchemy. Mm-hmm. And then he brought up this phrase that Jordan Peterson has used quite a bit, the solve e coagula, dissolve and then recoagulate again. Mm-hmm. And the minute I read that, I remembered something my daughter had told me about caterpillars. And I went and looked it up to see if it was true, and indeed it is. That when a caterpillar is in the, what do they call that beautiful thing that hangs off the tree?
Chrysalis.
The chrysalis. When the caterpillar is in the chrysalis, it actually completely dissolves into just a goo. Just goes all the way back down to just undifferentiated cells just in this goo. Maybe even past the cell. I don't know how far down it goes, but it just dissolves. And then it comes back together into a butterfly. But what scientists discovered was that anything that caterpillar had learned in the caterpillar stage was remembered by the butterfly in the butterfly stage. Mm-hmm. You know? So whatever... I don't think consciousness is only a human function. And consciousness is not a mechanical function, because if it were, that kind of thing couldn't happen. If what a butterfly is experiencing is consciousness. And what I thought about is that the butterfly, what the butterfly learned as a caterpillar is still known to the butterfly, but the caterpillar will never learn what the butterfly knows. Mm-hmm. Right?
Yeah.
And so if a butterfly could talk to you, they'd probably say, well, yeah, it was very unpleasant being in that chrysalis and turning into goo and all of that. But and it was even kind of unpleasant being a caterpillar and having to go and eat so much of that horrible grassy stuff that I had to eat and crawl along the way. It was pretty unpleasant. But now that I look back on it, mm-hmm. I understand why that had to happen and what the process was. And so it has a meaning for me. And so the new thing that the butterfly experiences now that's so beautiful, it kind of rewrites the difficulties of the caterpillar stage. Mm-hmm. And that's part of what I think, part of what consciousness does is it creates this frame for us. It allows us to frame. I don't know if that says anything.
Okay. Yeah.
That's what I've been thinking about.
Well, we have a lot of work to do deciphering Wolfgang Smith's stuff in the next week. Try and keep in touch. But
yes, but anyway, you were saying that information is not just
Not ones and zeros.
Not just ones and zeros. And you also said that math in computation is not just about numbers. Now, that's what you meant when you were saying that even a musician reading a piece of sheet music is doing a computational function.
Right. Set of choices guided by a set of rules. And so, yeah, the sheet music is the source code. It's a formal language. I mean, people always talk about formal versus natural language, and that somehow formal languages are not really, good enough for human consumption. But yeah, blueprints for building a schematic, architectural drawings for a house. I think you probably go through the same process with your art. It starts out as maybe an idea, not really fully formed. And then you sort of take steps in the direction, and you have an intuition that says, no, that's not the right direction, or this one, okay, I'll keep going that way. Am I close?
Well, yeah, I mean, I think it's it goes back to this whole notion of fittedness. You, in some of our earlier conversations, we talked about the lock and the key. The lock is already a something that has a certain confirmation to it, and the key can be revised in different ways so that it will fit that lock. You can take the key and you can file it down and make it fit that lock, but there has to be a fittedness before the tumbler opens.
Right.
And I think it was John Vervaeke made the comment that constraint is the fittedness of the evolutionary process. And so so evolution is a kind of a computational process of some kind, because it's within the constraints of the environment, it is developing fittedness. So
yeah.
In some way, it's mapping reality.
Well, you're exploring the unexplored. So as a hardware designer in electronics, I go through the same process. You start out with a design review meeting. Somebody shows up, they have some ideas on scratch paper, on notes. You talk, you get some vague idea of what they want, the customer wants. So I worked in the area of contract engineering for a while. So you deal with a client, they have an idea, they want you to engineer it. And then the place I worked for, they would bring in a team of engineers with different expertises depending on what the project entailed. And so you're starting from scratch. It's just ideas. And then I throw things out, what processor would be a good choice? How do I instrument analog? You don't know where you're starting, but you throw stuff out, and then it kind of, well, no, that doesn't work. This works. And gradually, by trial and error, and you erase stuff and you try something else, and it kind of tells you what it wants to be as the circuit design goes on, until finally you actually create a circuit board and programming, and you can return the client a board ready for clinical testing or whatever they wanted to do. But I don't go into a project I didn't, knowing what I was going to do. And there's that guess trial where you're somehow probing the unknown. And by each test, you gain a little bit of information and you keep moving forward. And so I somehow imagine that's how the top-down causality is working. That's how the space of possibilities that have yet to have been created affect us by us probing them, asking questions, getting answers, and then kind of random walking our way towards a creation, which takes an idea and turns it into a physical reality. So yours starts out as an idea, something you might want. I'm guessing. I don't want to put words in your mouth, but it ends up in a painting that captures emotion, thoughts, which now you can share with somebody else and experience. So computation doesn't just produce buildings and electronic circuits, it produces works of art and pieces of music, which then go on to affect people at an emotional level.
So if we boiled it down to its essence, computation is a seeking fittedness, basically.
Yeah, I guess you could say that. Exploring the universe, and somehow the universe talks back to us and shows us things that we've never seen or experienced before.
Yeah, so in my conversation with Esther Meek earlier, when we were talking about knowledge, knowing, she says, you know, when you're open to reality with the trust that reality is good, reality will come back and give you more gifts. And so it's always that kind of seeking, that exploring, that attempting to touch, be like the blind man trying to tell what it is that he's touching, and then bringing that in, and then keeping moving towards instantiation. So it's a kind of computation is a kind of seeking fittedness, I guess. So part of our problem is that we automatically, there's been so much talk about the simulation that the minute we hear computation, we think, oh boy, they're trying to turn the world into a simulation. But computation is just a word that describes an action, right? And
Right.
The old philosophers used to talk about potentia and actus, the potential and the act. And so the potential, the way I see it, if we lay it out in simple terms, the potential is what we tend to think of as our material universe here, broken down into particles at the quantum level, where it's just all potential until it's observed. And the observation is the act. And so the act turns the potential into reality.
Bingo.
Right? So potential and act meet in union. Potential and act create a unity, and that union is the vertical causation.
Something out there is guiding you when you make your decisions on painting. What is it?
Yes.
Yeah, that's fascinating to me, is how we're in touch with something beyond us. And if we make the right choices and we have faith and we're not afraid to fail.
Well, one of the other things that I think it was David Bohm was talking about is necessity and contingency. And he was saying necessity is what cannot be otherwise. So if you have a feather and it's in a vacuum, it will just fall straight to the ground. That's a necessity. But if you have a feather and there's any breeze blowing, the trajectory of the feather is contingent upon the way that the breeze blows. So the way I read that is that the contingent is dependent on context. And so making a painting is context all the way down. Every single stroke changes the context so that the next stroke is contingent upon all the strokes that were already laid down, plus whatever is in your consciousness as you're working. So it's just this constant interplay of context and contingency, and there's no necessity there. So I don't know what happens when there's something that isn't happening necessarily. Or is it that the only time anything happens necessarily is when it's in a vacuum? I'm not the physicist, so I had never heard that whole thing before.
No, everything is a sequence of choices. It's at some level. This is where I want to get back to Wolfgang Smith's first paragraphs about the cosmic time, the boundedness of it. Because we talk a lot about the observer, the role of measurement. But at some point, the measurements, the observer has to act back on the universe. A zombie observer just watching everything really doesn't add anything to the physics or the universe. It's only when the observer acts back on the world around it that things happen. We don't focus in physics.
So it isn't just the act of observation then. It's not just looking, it's seeing.
Mm-hmm. And that turns into an action which changes the universe somehow. There's a loop there. There's a completion that the observation starts, and there's a point when something is done, and he talks about it, a distinction in time that sets the completion of something. And that is whatever it was doing, it's done. It's finished whatever has happened. And that is a cosmic time different than the clock time. It's a clock time of events and starts and finishes. And we don't focus in physics on that final step when something acts back. And I always use the word choice, and I know it bugs a lot of people, but I still haven't found anything better to use, though I'm open to suggestions. That at some point the observations turn into a choice where the system that's making the observations acts back on its environment. The process of observation is always quantum mechanical, because at that level of reality, electrons, forces, and everything's quantum mechanical. There's a classical phase, a phase in between, where the quantum nature is erased. Somehow the system acts back on its environment. Again, that happens at a quantum mechanical level. And but what happens when you go back? We don't spend any time looking at that. And I think Wolfgang Smith is poking at that. I don't want to put words in his mouth, but I think he's getting his hands on that's an important part of the whole process that physics is missing. Now,
so let me try to understand what you're saying in terms of a specific. We know one where they determined that this observation part is really essential was in the double slit experiment. So the double slit experiment, they've done a number of iterations of that in various ways, and I know that's created a lot of consternation, but basically when they're shooting the photons through the double slits and they get this wave pattern, they recognize that light is both a wave and a particle. But the act of observing the wave actually, well, I'm misstating, I guess, but if you take any one of these observation things, it's part of what sets up the observation is first there's a question. The only reason I want to observe that is because I have a question about it. Mm-hmm. So is it the question that is acting on the system? Or is the observer actually doing something after the observation? Is it the observation itself that acts on the system? Or are you saying that there's something subsequent to the observation that changes the system?
There's a whole Alice through the looking glass world. The experiment you need to focus on is called delayed choice with quantum eraser.
That's the one I was thinking about, but I couldn't remember the name of it.
Yeah, and it's a short paper. I think it's maybe 5 or 6 or 7 pages. And I probably read through it at least 40 or 50 times. I don't think I'm smart, but I'm very persistent. it took me that long to finally have the aha moment on it. And at that point, I understood why John Conway called the theorem the strong free will theorem in quantum mechanics. And I don't want to go off on it, but I'll tell you the PBS, the TED Talk versions that you'll get on YouTube telling you the nature of experiments get it wrong. And I thank the good Lord at this point that I'm an experimentalist, because I could look at the experiment as it was described, and I realized what they were doing experimentally is not what the paper says they're doing. And what the experiment is even more profound in its implications than the theorists were getting at. But this is probably a story for a whole nother day.
Well, I was wondering, do you have time that I mean, on another day, could we just explore that one experiment in terms of these issues related to time and concretization and all that?
Well, the punchline is that one of the ways out of the whole quantum mechanical enigmas is to say that in the quantum mechanical world, there is no past and future, no here and there. Everything is instantaneous in the quantum mechanical world. So our ideas of past and future and measurement don't apply in that world. So if the electron does something, it's because that's what the electron wanted to do. If the photon does something, that's because it wants to do. And it showed you what you get to see. I mean, that's one interpretation, and I think it's a fascinating one. That's why John Conway chose the name strong free will theorem, because it's almost as if, I believe it was a spin one particle in that case. It has a mind of its own. Mm-hmm. And we see what it wants us to see, not, it's the world of Toy Story, you know? It's like the toys have their own universe and their own interactions, but as soon as a human opens the door, all the toys just freeze. Uh-huh. But then when the human stops looking, the toys have this. That's the quantum mechanical world.
Oh, that's such a beautiful analogy.
And so we as classical observers are the adults in Toy Story. And we're trying to figure out what the toys are doing by only glimpsing it every once in a while when we open the door and see them all frozen in place. So you can come up with all sorts of scenarios that fit the momentary observations we make. And one of them is you can either have the future can change the past, or the quantum world doesn't respect locality at all. And I'm tending to go with that one as I age, and I don't have to do math and homework anymore, so no one beats me up by thinking different thoughts.
Well, okay, so if the quantum world doesn't respect locality, then that would almost imply, I always scare myself when I think things like this. In Wolfgang Smith's tripartite cosmos, there is the center, which is without space and time, and then there is the interior of the circle that's the intermediary, where there is only time and no space. So if the quantum doesn't respect locality, it almost sounds as though the quantum is somehow on that boundary between our visible universe and this invisible intermediary.
I'll have to think about that one.
Yeah, especially because the whole issue of quantum entanglement implies that the speed of light is irrelevant in terms of the interactions taking place between the particles that are, no matter how far apart they are in quantum entanglement, it's instantaneous. The change
for them, it's instantaneous.
Yeah. So that would also imply that there's no space in between them, even though there is.
Yeah. Well,
Which
that's
would also
that's
mean
the
that
implication.
they're in between somehow, in between the realms.
So I'm sure there's
Sounds like
theorists
I'm
out
writing
there
science fiction now, but
that have tackled this, and if I went on the archive, I'd probably find some papers that have
well, it does
taken
come
that
up
route.
as
But
it does come up as an implication in some of Wolfgang Smith's stuff. So I may, if I'm brave enough, I may ask him about it.
well, it tends to imply that the classic world is one that respects locality. The quantum world doesn't. The classic world is governed by cosmic time, more so.
The classic world is governed by cosmic time.
Yeah, I think that's how he's using it, as events. We mark time by events. This happened before that. There's in math, if you go to the sub basement in abstract mathematics, you get to the notion of ordinal and cardinal numbers.
Mm-hmm.
We
We
tend
learned
to
about that when I was in school.
we confuse them, in popular usage. But cardinal, when we use a number in the cardinal sense, it's referring to size, which I correlates with Wolfgang Smith's notion of time in the sense of measure. But a number can also mean in the sense of ordering, first, second, third. So that is what I would say Wolfgang's cosmic time is, where time is we're using it as order before and after.
See, I think he and Wolfram need to talk to each other, because that's Wolfram's definition of time. Is time is not what we think of as time, but time is the updating of events. And it's not so much that this happens and then that happens. It's just wherever the updating is ready, it updates that thing. And so, yeah, I think they could talk to each other.
Well, here's where I get fascinated. Well, I haven't really gotten past the first couple paragraphs in that paper, is that for there to be a boundary, a mark, that cosmic time that marks the end or a boundary of an event or something, there has to be a way of marking that boundary. There has to be a way of telling what was before and what was after. Now, if you go into physics, physicists talk a lot about symmetries, and it's a buzzword you hear a lot. So people always see physicists doing equations, grinding equations. Do you ever ask where the equations come from? And those come from the symmetries. The symmetry tells you that something before is the same as something after. So you can write down an equation of state for energy or for momentum, and you know that because of symmetry, after is the same as before. So you now have the same equation of state in a different realm. You can put the equal sign between them and now solve for variables. But in order for this cosmic time event to happen, something has to be different after than it was before. So it's kind of the opposite of symmetry. Now, after and before are 2 points in time. Now bring them together. There has to be a boundary point that crossed over where the symmetry of whatever you're looking at changed. Before is no longer after. In a world which is continuous,
Yeah. Okay. Now,
that can't happen.
Yeah.
In a world where the laws of physics are continuous and differentiable functions, you can't do that. The only way to break it is if the universe somehow is finite, that there is a definite step across. Now we're back to Zeno's paradox of the arrow in flight. I have no answers on this one. This is as far as I've gotten.
Well, so this might, I'm going to throw this in here just to end, and then we'll continue on this train of time and yes and no questions and all that, because I think this is really valuable. But just for that question, it might help to think about Matthew Pageau's concept of time, because his concept of time is that it is continuous, but it's not continuous in the sense of being complete, that there is no differentiation along the continuous band, because he says if it is all inclusive, if it's complete in the sense of being all inclusive and that there's no differentiation, then there's no way to have dark and light. There's no way to have male and female. All of the things that are vital to the construction of our universe, there has to be a way to differentiate along the polarity. Nevertheless, it's continuous in the sense that it he lines up time with chaos. And so it's all potential. So Wolfgang Smith, I think, is saying that space is the potential and time is the act. But I think that Matthew Pageau is saying that time is the potential and space is the act. So I think there's a lot to explore there, and I'll make some notes and send them to you, and maybe we can talk about that in the future.
Poor me, though, coming from physics, I can't quite go there.
Well, he does have some things in there that I think might relate to physics, but I can't drag them up into my brain right now because we've been talking a long time. But the Toy Story analogy is so great. Was that original to you, or did you pick that up from somebody?
Yeah, that's my feeble attempt to try and explain quantum mechanics to people.
It's not feeble, though. It's just perfect. I mean, it almost sounds like the movie was made to describe quantum mechanics.
And I think that's one of the struggles in the field of physics now, is the math has been so good and so accurate that people are afraid to walk away from it. But it's a good question, and it might be something Wolfgang Smith would tackle, is that how much of what we consider physics is just an artifact of the mathematics we're using to model our physical world. You know, the old saying that the map is not the territory. The model is not what the universe is really doing. We've had some very successful mathematical models that people are reluctant to walk away from, but
yeah, he has quite a bit to say about that later in the article. So
yeah, I have the sense that he's there.
Yeah,
I haven't. So
yeah, if you get further along, you will see that. But that'll be a good question for me to ask him about the symmetries. What happens at that break between the before and the after if it's not symmetric?
Well, and if the universe is perfectly deterministic, then there can be no boundary. There's no point. So if there is a boundary, then something about the universe has to have changed. The possible futures have been filtered out and one selected. And so a choice, as I use the word, assumes that the universe is not perfectly deterministic. The laws of physics don't perfectly describe the next future. There is a choice. There is a moment when there is a fork in the road and we can go one way or the other. And sometimes that just happens by random, at the quantum mechanical level, the probabilities. But if you consider, we use the word intelligence, I think, as a noun, and we should probably use it as an adverb. I think that might help a lot. So stop looking for intelligence, but look for processes that act intelligently. An intelligent process is one that can be described by an algorithm or a set of rules versus simply quantum mechanics where things happen by probability. So then you can look for intelligence. Any physical system that can mimic a set of rules, resulting in...
That's exactly what Wolfram is doing right now in his, he puts these process team meetings online, and he's had several recently on molecular computation.
Mhm.
I listen to them just for background noise because I only catch maybe 2% of it. But when I do catch 2%, it's like, oh my gosh, they're going there. And that's exactly what he's doing. He's looking for processes that act intelligently within the within the chemistry frame or within the biology frame. And you can tell from the question, he's talking to chemists, he's talking to biologists, and he's trying to figure out how these things might fit with his model. And the questions he's asking them have this implication all over them. So yeah, very cool. This has been great, Glenn. Obviously, we need to talk more often because now that we got started, we can't stop.
Yeah, I haven't even gotten to my handful of notes that I have down.
Well, then we'll have to do that next time. I think
Okay.
we needed to get this out there so that we kind of knew what part of the territory we're exploring, because since last time I talked to you, I've read numerous books and articles, and you have too. And so we're both, we got to line up our spaces.
So I'm still stuck with Robodog, and that probably will keep me busy until summer.
Oh, I thought that you had moved on from Robodog. You went back.
No. I was playing with cellular automata for a while, and I got through that.
Okay.
I had an inspired solution, and so saved me what I thought would be a long time. Yeah, so the Robodog is just an excuse to play with natural language, to see if I can teach a dog how to understand human speech.
Uh-huh.
It's just my personal challenge to see how far I can get with it. So that's taking me down the road of language and how it works.
To see if you can get your robot dog to understand natural language.
Yeah.
Have you by any chance seen the videos where they're teaching a regular dog to talk, to learn a natural language?
I haven't run across that.
It started with this young woman who just decided she wanted to give her dog a chance to communicate with her. So she got a bunch of pressure activated buttons on the floor that made that she could record a sound with. So the dog would hit that and it would say door, or it would say potty, or it would say, bone or something. And she set up some different ones on the floor, and they're all in a unique configuration so the dog can tell location. It's kind of like playing concentration. And then, so for me, it's a little hard of knowing whether she's the one who got trained or whether the dog is the one who got trained. Because obviously when the dog hits the bone button, she goes and gets a bone for him. So he knows that means bone, but then he also knows that anytime he hits that, he can get a bone from her. But he is apparently learning language because he knows which buttons to hit to get what he wants, right?
Well, the catch is that, if they express an emotion.
She has some pretty complex ones, like some of them are like some of them are like hungry, some of them are like sad, and then once she did that, a whole lot of other people started doing it. So it kind of open source, because she showed videos of it, and so it's kind of open sourced all over the internet, and a lot of people are doing it. Very similar to what happened years ago when some parent decided that it would be helpful to teach infants sign language so that they could communicate what they were feeling even before they could talk, and then they wouldn't get so frustrated. And it was quite effective. And so then it just extrapolated out, and now, like most parents, I guess, are doing that. But yeah, I'll see if I can round up some of those videos and show it to you.
Okay. Well,
I know a human dog is different than a robo dog, but anyway. I don't have much to offer in the realm of physics, but I can always offer you that.
But it does occupy me a lot. It's true.
Good talking to you, Glenn, and I hope we get together again soon.
Okay, it's been fun.
Yeah, okay. Bye-bye.
Take care.